So reminder for the overview, we're going to have another quiz on Friday. Homework 2 due on Friday. We're going to have another homework 3, and then we're going to put a rest on the assignments to get ready for exam 1. So 2 weeks from Friday is the first exam. Now remember, this is going to be the material balances component of it. So if you don't do as well as you would have liked on this one, do not despair, do not give up. Go back, refresh, because on the final, there'll be section 1 of the exam, and if you do well on that, I average the two together, right? So it'll only help. So if you bomb the final, right, it's only going to hurt you in the final percentage of the grade. It's not going to boost your grade 1, right? But if you do really well on the final, you'll boost your exam 1 score and your final score, so it's a huge boost to everyone's grades. 1 week from Friday, so in anticipation of the exam, I give out the practice exam, right? So last year's actual exam in class, right, the week before the actual exam. My recommendation is that you sit down and you take it in the 50 minutes that we have here, just so you have an idea of the time crunch and pressure. Right? My exams are notoriously demanding on time. But if you are proficient with your reading of problems, drawing correct process flow diagrams, and writing out your material balances quickly, you'll be fine on the material timeline. The key thing here, though, is do not hesitate to write out your balances. Right? You may not necessarily know how to solve the problem completely, but if you just write out all the balances, it'll probably take you 30 seconds. Right? So if you write out all the balances, seeing the equations, you're like, okay, I know what to do first. Right? So instead of thinking about what's the most optimal, efficient way of doing things, sometimes it's just going to be quicker to write out all the balances and then find out which equation has 0 degrees of freedom. Does that make sense? But I don't force everyone here and chain you to your chair. Like if you want to just take the practice exam and go, you can, but I really recommend that you stay and try and take it. Yes?
Do you expect us to do the degrees of freedom analysis on the test?
No. I don't even expect, unless I say balance the whole process, you don't even have to balance the whole process, right? Just get to the objective and end at the objective. So for example, one of the first examples we did was how much ethanol is lost in the bottom stream. Once you answer that, you're good. You don't have to balance the rest of the thing out. Right now, you can balance the whole process out and then use a total mass balance to double check you got it right. So that's always a tool available. But for the exam, I just want you to get to the right answer using all the tools at your disposal. Any questions?
So this Friday, we'll have the practice exam.
Next Friday.
Next Friday.
Yes. So we're going to have 3 homeworks under our belt before we perform the first exam. If I've got my timeline right. But a quiz on Friday. But then next Friday, no quiz. All right, as you can see from the display, not the folks at home, we are doing reacting systems now, okay? So we've covered mass balances on non-reacting systems for a single unit operation. Last class, we did mass balances on multiple processes, right, where we can combine total balances and balances on each individual step to help us solve our problems, okay? Now, we've only done a small number of examples, so the complexity is going to increase quite rapidly in the class now. Once we start throwing in thermodynamics and energy balances, the complexity will grow even faster, okay? So what I'm showing you here is the individual processes, but then you're going to have to combine them in different ways, right, to balance more complicated processes that you'll see on the homework and that you'll see on the exams. So as a recap, if we have a general reaction, so let's do now, some of this you may have seen in a chemistry class or an earlier engineering course, but I'm going to go through a couple of quick examples. So if I write mu lowercase a plus mu b going to mu c plus mu d, right? So A, B, C, and D are chemicals. This is some arbitrary chemical reaction. I'll use a real example in just a moment. Does anyone recall what these values are called? Stoichiometric coefficient. And I don't have it in my notes, so I'm going to botch the spelling here. I'm going to spell check that one. So this is the stoichiometric coefficient. So if I were to put out a reaction, the Haber process, by which I believe something like 70% of our body's nitrogen comes from. So it's a big deal. Right? So we take nitrogen, react it with hydrogen, and we can synthesize ammonia. This is done at very high temperatures and pressures. This is a Nobel Prize winning chemical process, and it is the reason why we have, like, what, 8 billion people on this planet? Without this, we would all be doomed. Okay? So, what is the stoichiometric coefficient for nitrogen?
1.
Is it 1? 1 is almost correct. It is actually -1. Right? Because the way that I've drawn the reaction, I am consuming nitrogen to form ammonia. So then the stoichiometric coefficient for hydrogen would be equal to what? -3. And the stoichiometric coefficient for ammonia, I'll just write A, is equal to what? 2. Now I could rewrite this reaction as 1/2 nitrogen plus 3/2 hydrogen goes to 1 ammonia, in which case all of my stoichiometric coefficients would be modified. Doesn't matter. What if I were to draw this reaction in reverse? Ammonia goes to nitrogen and hydrogen. I would just change the signs here. None of that actually matters. If you follow the systems that we're going to detail, it doesn't matter which direction you draw it. Right? Just be consistent. Anything on the left-hand side is a negative. Anything on the right-hand side is a positive. Even if we know the reaction goes one way or the other, sometimes you may not know necessarily what the equilibrium is, and the reaction could actually be going backwards in the process. But as long as you draw the reaction a certain way and you use the correct positive or negative stoichiometric coefficients, you will be okay. Now, when we're considering a material balance on a chemical reacting system, when we considered non-reacting systems, we said we'd have 1, 2, 3 independent species. Are these now independent species? They are linked together. So if I change the amount of nitrogen, I must change the amount of hydrogen, and I must change the amount of ammonia. These are all now linked together. So I know in general chemistry, and you may have seen it in your earlier chemical engineering classes, chemical reaction equilibrium. So remember, like a KSP for how much a salt dissolves, right? Or a Ka in your chemistry or organic chemistry class. Right, we can write out KEQ, which is an equilibrium constant, right? And this is something you can usually look up in a book. In your thermodynamics class, you'll figure out how to calculate this. For an ideal gas reaction, which is the most complex that we're going to do for the purposes of equilibrium calculations, we can write out the equilibrium constant. Does anyone remember what capital Pi represents mathematically?
Isn't it like a sum of like products?
Exactly, it is the product sum. It is Y sub I, which is the mole fraction, raised to the power of its stoichiometric coefficient. Again, so if you botch the signs, you get the direction of the reaction wrong, it doesn't actually matter, right? So in the case of the Haber process, this would result in ammonia has a positive stoichiometric coefficient, so it's in the numerator. So it would be mole fraction of ammonia squared. And then the left-hand side of the equation, these are negative stoichiometric coefficients, so they'll be in the denominator, right? Because this is the product sum. I'm multiplying the mole fractions raised to the power of the stoichiometric coefficients for all of them. So some are positive stoichiometric, some are negative. So this would be YN2 and then YH2 cubed. Again, let's look at the degrees of freedom. So if I was given an equilibrium constant, I can't actually solve this equation because I have one equation and 1, 2, 3 unknowns, right? But they're all linked together. So how do we link these together? We use something called the extent of reaction. Now, you'll see the extensive reaction written a couple of different ways in terms of nomenclature. The common one is this awful Greek letter, xi, I think it is. Right? So sometimes I'll do this just for the satisfaction of drawing it well in my notes. But in general, I'll just do like a big X or something like that. Right? So depending on which one, this is like the conventional nomenclature in a lot of chemical engineering textbooks, but it's a little awful to write. Was that?
It's like a cursive Z.
I think it's Xi or Psi? Is this one? I remember. Who's good on the Greek alphabet? I think that's the one. Anyway, it's a terrible letter. So we can use it. We can use it if we want to feel fancy. Oftentimes in my personal notes, I'll just use big capital X. Okay. All right. So how the extensive reaction works is we can define it as the number of moles of species I with a 0. So we call that initial. Ni naught is how you would read that out to someone if you were describing this equation. Plus the stoichiometric coefficient. Oops, sorry. Right, I botched this equation. Never mind. Ni minus Ni naught over the stoichiometric coefficient. This is how we can define it. The other way that we can write it is that the number of moles of species I that exist in the system is the number of moles of species I initially plus the stoichiometric coefficient multiplied by the extent of reaction. So this is a way that we can link together all of the different species. Then we can also write that the mole fraction of any given species is the number of moles of that species divided by the total number of moles in that particular process. So in the example of the Haber process, if we wanted to apply the extensive reaction to help us solve this particular system, we could write out that the number of moles of hydrogen is equal to the number of moles of hydrogen initially, NH2 naught, minus 3 times the extensive reaction. So what this extensive reaction means is every time you go from the reactants to the products, right, that's 1 moles worth of extensive reaction, right? So this has units of moles or moles per second if you want to think of it in terms of a continuous flowing system, right? An open and steady state system. Yes?
So it's like every unit of reaction?
Every chunk of these. So if I take a mole's worth of the reactants and I make a mole's worth of the products, that amounts to 1 mole's worth of the extensive reaction.
So if you change the stoichiometry, use fractions like you said before, does that change the...
It will change what the extensive reaction is, but it will not change the final number. So let's say, for example, I were to rewrite this as 1/2 nitrogen, 3/2 hydrogen goes to 1 ammonia. That would modify all of my extensive reactions, right? Instead of having 3, I would have 3/2. But what would change is that my extensive reaction would have to be doubled, because I'd have to take twice as many half chunks to make 1 chunk. Right? And if I get the direction wrong and I drew the reaction backwards from what's actually going on in the process, no big deal, I'd get a negative extensive reaction. Right? And that would fix all of the signs of my stoichiometric coefficients. Right? So everything will work out as long as you don't screw up the signs. Right? Everything on the left is negative, everything on the right is positive. You can have a negative extensive reaction. Don't panic. This is a scenario where that Excel solver, make the non-constrained variables non-negative, that one can screw you up. Is there a question I saw popping up maybe? Okay. All right, so for hydrogen, for nitrogen, the number of moles of nitrogen would be equal to the number of moles of nitrogen initially in the system minus 1 times the extent of reaction. And again, see, I can't draw it well. And for ammonia, it would be the number of moles of ammonia initially plus 2 times the extent of reaction. So if I had a positive extent of reaction, I would be consuming hydrogen and nitrogen, and I would be creating ammonia. Now, depending on the system, you may not necessarily have any ammonia fed to the system, in which case this would be 0. Right? But now we have a system of equations that we can all substitute in. Now, the final step is I add these all up so I can have the total number of moles in the system at any unit of time or set time, number of moles total initially. Right? So in this case here, I'm consuming 4 moles and I'm making 2, so the total number of moles is not conserved. Okay? So I add up everything that's initially in the system. I want to figure out how much is in the system at any given point. And so then I just add up all of these terms right here. So I have minus 3, minus 1, so that's minus 4 plus 2, minus 2 times the extent of reaction. So for every chunk of an extent of reaction, so a mole's worth of extent of reaction, I am reducing the total number of moles in this system. Right? That makes sense because I'm consuming 4, I'm getting 2, right? It all makes sense now. So if I wanted to calculate what the mole fraction is, I could do the mole fraction of hydrogen, which would be equal to the number of moles of hydrogen divided by the total number of moles in the system. And so then I can just apply this here, and I get NH2 initially minus 3 times the extent of reaction divided by the number of moles total initially minus 2 times the extent of reaction. And I'll just do the same thing for the nitrogens and the ammonia, N2 initially minus the extent over N total initial minus 2 times the extent. And for the ammonia, it would be ammonia initially plus 2 the extent divided by NT initial minus 2 times the extent. Okay, so now we can solve our equilibrium equation, right? I have one equation, K equilibrium is equal to some numerical value that we can calculate from thermodynamics or we can look up. And I have the right-hand side, which is all as a function of mole fractions. If we look at our mole fractions, right, if we know the initial specifications of our system, the number of moles of every species initially, we can get number of hydrogen initial, number of total initial, number of nitrogen initial, number of ammonia initial. I only have one unknown, and that is the extent of reaction. So then I solve for the extent. Once I solve for the extent of reaction, I can substitute it back into these equations, and voila, I have balanced my reacting system process. Now we're going to go through this example with a little bit more detail and a couple of other strategies. So the extent of reaction, I like to start off with it because it highlights that chemical reactions and the species that participate in those chemical reactions, they are dependent upon one another. So it is a different class of problems. It's not as simple as just one balance per species. That works for non-reacting systems. It doesn't work for reacting systems. So we have to take a slightly different strategy. All right, so a few definitions for reacting systems. And this is the way that you're going to be communicated the design specifications for the reactions. Now, in the real world and in the junior year, you're going to be calculating what these design specifications are based on, let's say, for example, the reactor kinetics and reactor design course, right? But for the purposes of this class, it's going to be provided to you. So yield means the moles of desired product over the moles formed in a perfect world. Right, so this would be if there's no side reactions, no kinetic limitations, no thermodynamic limitations, right? This is the yield, this is what you're actually making versus what you could potentially make. Selectivity moles of desired product over moles of undesired product. So an example would be A going to B and A going to C in a competing reaction. The selectivity would be number of moles of B potentially over number of moles of C if this is the one we want. So a higher selectivity means that you're creating more of the desired product. And the one that you'll see the most often is conversion. And this is the moles reacted over the moles fed. Okay, so if you have 100% of, let's say, for example, your nitrogen reacting, better yet, hydrogen would be the limiting reagent in this process because nitrogen is basically free because we get it from the air. Right, so hydrogen would be your desirable limiting reagent because it's the one that costs the most money. So your conversion would be if 100% of your hydrogen reacted to what is fed, that means your conversion would be 100%. If none of the hydrogen reacted, you'd have zero conversion. Right, the way that I implement this is that the conversion will be equal to the number of moles in minus the number of moles out divided by the number of moles in. Right, so this one's easy. Number of moles in is equal to moles fed. That makes a lot of sense. Right, the difference between how much you feed and how much you take out, well, it had to go somewhere, right? That's how much is reacted. Right, so it's the same thing, but this puts it into a math form that you can actually use to solve your problems. Now, oftentimes, I will forget this equation, right? Seems simple, right? But I can always just refigure it out, okay? So if I have 100% conversion, everything is reacting. So that means I should have nothing coming out, right? So n minus 0, n over n, that's equal to 1. That's 100%, right? So I just kind of double check. If I have 0% conversion, right, that means that the amount that I feed is exactly what's coming out of the system because nothing reacted, right? So then n minus n over is 0, right? So that gives me conversion of 0, right? So that's the way that I double check all these things. Okay. Any questions so far? We're going to do examples. So this is another one of these resources that you have in the Canvas page. There's going to be 3 ways that I'm going to teach you how to solve reacting systems. Okay, so there's an atomic species balance. We haven't gotten there yet. Extensive reaction, I've previewed that, so we'll do that again. And then this one right here, the molecular species balance. This is what all of you will most likely default to in a panic because it's the strategy that you kind of understand, right? So the way to think about this one is if I have the Haber process, right, if I am forming 2 moles of nitrogen at a certain rate, what is the rate that I am consuming nitrogen and hydrogen? Right? Kind of makes intuitive sense. That's how we would have kind of sussed it out in a chemistry class. I'm here to tell you that this is only reasonable in a very simple system. For most all the processes we're going to want to do, the extensive reaction and atomic species balance are going to be the ones we want to do. Okay? So I will start off with the molecular species balance and show you, if we want to do it rigorously, how much of a pain it potentially is. Okay. So I'm going to use this board here to draw out the process, and then we're going to balance it using multiple different ways. Okay, so we're going to follow the Haber process. Coming into the reactor, we're going to have 100 moles per minute. Right? It's going to be at the stoichiometric ratio. right, just to make things a little bit easier. Now, in the real world, we would never feed this at the stoichiometric ratio because we would want to drive the reaction forward by having excess reagents. If I'm going to choose one of these two to be excess, I'm going to choose the nitrogen because it's free, right? But for the purpose of this one, we'll make it stoichiometric. So that gives us N of N2 into the system is 25 moles per minute. And for the hydrogen, it is then going to be 75, so that we have a 3-to-1 ratio that adds up to 100, just to make the numbers nice and easy. Okay? Coming out of the system, we're going to have our unknown of nitrogen, our unknown of hydrogen, and our unknown of the ammonia, so N2, H2, and Na. We're going to get one last piece of information, and then this is a 50% conversion. Now, normally, if you were given the information of 50% conversion, we would specify what species is being converted. But since this is in a stoichiometric ratio, it's the same. Right? So I can say 50% conversion of hydrogen, right? Because it's the limiting reagent, that's the one that we care about. Okay, so with this information, balance the process. What is the outlet flow rates, or what is the outlet composition? Okay, so we're going to start off with the molecule balance. And we'll show you why it sucks. Okay, are moles a conserved species?
No.
No, right? Because obviously we're losing moles in this chemical reaction. So that means my molecule balance, I got to take the full shebang of the general balance equation. In minus out plus generation minus consumption equals accumulation. So in this case, we're going to assume open and steady state, so we're not going to have any accumulation. That saves us a little bit of hassle. Let me ask you an alternative question. Are atoms conserved? Yes. So can I have a generation of carbon atoms in this process? No. That's why the atom balances are much nicer. They're weird, but they're much nicer because I don't have to deal with this consumption and generation garbage. Okay, so let's write out our balances. So for N2 balance, into the system, I have 25 moles of N2 per minute. Right, so in the interest of time, I may truncate some of my units here a little bit. I'll try and keep them clear where possible. Coming out of the system, sorry, I'll write this here. So let me simplify this one a little bit. So in the nitrogen balance, which of these terms can I cancel out? Am I generating or consuming the nitrogen? I'm consuming. So the generation here, so I don't have to worry too much about that. So I'm going to put equals to what comes out, which is our unknown. And then I'm also going to write rate of N2. So this could be the rate of formation, it could be the rate of consumption, it could be a positive number, it could be a negative number, right? So right now I can't solve this balance, right? Because I've got two unknowns. I don't know how much is coming out, and I don't know what the rate of change of the nitrogen composition is. So I'll do the hydrogen balance. So I have 75 75 moles of H2 per minute. Leaving the system, I have my unknown plus whatever the rate of change of my hydrogen is there. Yes?
So why couldn't we solve the rate of change? Given the conversion ratio, could we use that for the...
We can at some point, yes. So we'll have to include that design specification. Oh, so let's go over the degrees of freedom really quickly here. So molecular species balance, we have 3 unknowns plus 1 independent equation minus 3 independent molecular species minus 1 design specification, which is our conversion, right? 3 unknowns plus 1 equation is 4, minus 3 independent molecular species, which is the 3 nitrogen, hydrogen, and ammonia, minus 1 design specification. So we have 0 degrees of freedom in this one. But let's just finish out all the balances, and then we can go about solving them with the conversion piece of information. And for the ammonia, we have nothing fed to the system in, right? So we have the flow rate out of the system is going to be equal to the rate of ammonia generation. So this is out equals gen. Okay. So what we can do here is, if we have 100 moles per minute coming in and half of it is being converted, the way that I solved it here is to start with the ammonia for the conversion, right? So I'm going from, in this case, 4 to 2. So I'm consuming half of my material. So if I had 100% conversion, I should expect to have here 50 moles of ammonia, right? But I only have a 50% conversion, so that gives me that I have 25. So a 50% conversion right, 25 moles of ammonia. Now we could solve it using the in minus out over in with one of these other equations here, but just for the sake of, you know, the molecular species balance works well when it's just a simple system that we can kind of just work out. Okay. So that information now tells me what Na is equal to in this particular process. Now the hard part of the molecular balances is I have to relate the rate of formation of ammonia to the rate of consumptions or formations of the other species, and this is where it gets a little bit hairy. So what we can use is that the rate of change of one species divided by its stoichiometric coefficient is equal to the rate of change of another species divided by its stoichiometric coefficient. Right, so the idea here is sort of in the same thing with the extent of reaction. If you've got a higher stoichiometric coefficient per lump of stuff going from the left to the right, you'll have different rates. So let me just go through an example here with the hydrogen balance. So this is equal to our unknown plus, for every 3 moles of hydrogen consumed, we generate 2 moles of ammonia. And then we multiply this by our 25 moles of ammonia generated per minute.
Can you scoop it more?
Yes, I can. So this is the way to do it properly, right? And it's a little bit confusing. So from this here, right, we can kind of cross multiply. So let's say Ri is equal to stoichiometric coefficient of I, stoichiometric coefficient of J, Rj. So in this case, J is equal to the ammonia, and I is equal to the hydrogen. So I'm converting from the rate of formation of ammonia to the rate of consumption of the hydrogen. Does that make sense? This is why molecule balances suck. Okay? If you do it properly. The result is that we can get that the flow rate of hydrogen, if we solve this, is 37.5 moles per minute. And if we apply the same thing here, the only difference is it's not going to be 3 halves, it's going to be 1 half, right? For every 2 ammonias, we consume 1 nitrogen, as opposed to 3 hydrogens. Then we can solve for the number of moles of nitrogen, which is equal to 12.5. Okay, so we balance the process.
And that's the outflow.
That's the outflow, yes.
What if we do it improperly?
You can check with your mass balance. So you can convert your moles to mass and make sure that the total mass in is equal to the total mass out. Other than that, it's wrong.
Well, no, you're saying that molecule balances are like the worst way to do it if you do it right. What if you...
So molecule balances work in these simple scenarios where it's one reaction that's really well defined, not too complicated, but for most of the processes that we'll be working with, the atom balances and the extent of reaction will be a lot easier to do. So you can use it, and it is a useful tool, right? But this is the way that probably you would kind of figure it out in your own heads if you were doing this in, let's say, a chemistry class. Perhaps you haven't seen it done as tediously as this before, but intuitively, does this one make sense, right? We're generating some product. For every rate of generation of the product, there's a rate of consumption of the reagents. If it's more complicated, right, like in this case here, if I'm generating product C, there's a relationship to how quickly the rate of D is generated as well. It all kind of ties together. Is there a question or stretch? Okay. Okay. Now the new one here that we haven't seen before, so the extent of reaction one, let's just finish that one off. Okay?
So for the molecular species balance, do you need to have a conversion that reflected in your design specifications then? In order to-
Say that one more time.
If we're going to do the molecular species balance, are we have to have in our design specs a conversion ratio?
You will need that for all of them, actually.
Oh.
Yeah, so in terms of the degrees of freedom, if you can do one, you can do all. There are some circumstances where only an atom balance actually works, because for many of the reactions that we're actually going to be doing, we don't know what the chemical reaction is. So for example, what's the empirical formula for your gasoline? Does anyone know what the empirical formula for gasoline is?
Well, isn't it made up of a lot of different things?
Exactly. So for burning fuel, we don't actually know what the chemical composition is. We know what the atom fractions are. So what they do is they actually burn the fuel, and then they use a mass spectrometer to see how much carbon dioxide, how much sulfur dioxide, and how much nitrogen there is in the system. And then from there, they work out, after burning it in pure oxygen, what the carbon, hydrogen, nitrogen, oxygen, and sulfur content of that fuel is. So in that circumstances, we can't use an extent of reaction because I don't have a chemical reaction. We can't use a molecular species balance because I don't have a chemical reaction. But I can use this technique, atom balances, that we'll get to after we finish this off. So the extent of reaction is a nice, really useful tool. Right, so I have a couple of notes here. So molecular balances, simple systems with one reaction. And then I note, but even then, it's probably best to avoid it, right? Extent of reaction, I say use it when you need to do an equilibrium calculation, right? So if you don't know what the chemical equilibrium is, meaning that what I'm doing is I'm taking away something that puts you closer to reality, so you actually have to start figuring out the process, right? And that's how the real world is going to work. Just because I dump a bunch of chemicals into a bin doesn't mean they're necessarily going to react to completion. The equilibrium may only be a 5% conversion, right? So these are all the considerations that we need to make when designing real processes. And for atomic species balances, I say basically use this one as your default, right? And sometimes it's the only one that you can actually use. Okay, so for the extent of reaction, just to do degrees of freedom really quickly here. Number of unknowns is 3 that we're trying to solve for. We add 1 for the independent chemical reactions, okay? And then we minus number of reactive species, right? So that's going to be 3, the 3 different species that we have. If you have non-interacting something like argon or oxygen in this case that isn't participating in the reaction, you would subtract that because then you can just do a N equals out balance on the inert species. And then minus 1 for the design specifications gets us to 0 degrees of freedom. So the extent of reaction adds 1 extent of reaction as your unknown, but it's linking everything together, right? So on paper, it's technically more complicated because there's more math involved, but in methodology, It's very, very straightforward. Okay? So in this case here, right, we've got all of our balances written out in terms of the extent of reaction. The only thing we need to do is actually solve for the extent of reaction. So if we steal from our molecular species balance, we know that the number of moles of ammonia in this case is 25 moles per minute. We could use this equation here. We have 0 moles of ammonia coming in. We know there's 25 coming out. So the extent of reaction is then what? (12.5). So then the extent of reaction is 12.5. What are the units of my extent of reaction here? Moles per minute. So if I wanted to be super good on my nomenclature, I probably want to put extent of reaction dot to know that it's a flowing system. So from here, it's really trivial, right? I already got the equations. It's plug and chug, right? Nitrogen being, so instead of hydrogen, I'm feeding 75 minus 3 times the extent, which is 12.5, and I can get my outlet right there. And so then I should be able to just get number of hydrogen is 37.5 moles per minute, and the number of nitrogen is 12.5 moles per minute, right? So the extent of reaction, it adds an additional variable you have to solve for, which is the extent of reaction. But once you get it, everything just snaps into place perfectly. Any questions on that? Yes?
Which equation did we use to solve for the extent of reaction?
This one here. We could have used any of these ones, actually. But I just stole from the fact that we used our conversion to get the ammonia flow rate out. But we could have used the in minus out over in on any of these just to crack open what the extent of reaction is.
So extent of reaction is the same for all 3?
Yes, because they're all linked together, right? So if I consume any of my reactants, I have to form a product. And I have to consume my reactants in the ratio of my chemical reaction, assuming, of course, you have a balanced chemical reaction, right? So brush up on your chemistry if you need to balance your chemical reaction. So one of the things that we're going to be focusing on in the reacting systems is I'm going to say, here's your fuel, here's its composition, tell me how much oxygen I need to burn it, right? So remembering how to balance chemical reactions is going to be important here. But we'll talk about combustion on Friday. So we'll talk a lot. Combustion will be the bulk of what we're going to talk about for reactions. Okay, last one is the atom balance. Now for the atom balance, it's really nice because it's just like our non-reacting systems. It's in equals out. If I feed nitrogen atoms to the process, I get nitrogen atoms out of the process. We're not considering any nuclear events going on, right? So atoms are conserved, molecules are not conserved. So just quickly on the atom balances here, number of unknowns is still 3 minus the number of independent atomic species. How many independent atomic species do I have in the Haber process reaction? 2. I have nitrogen atoms and I have hydrogen atoms. So I can only perform 2 balances. I have no independent molecular species in there. This would be like an inert, like if there's argon in the system, which there is, right? There's about 1% argon in the atmosphere, minus the 1 design specification gets us to 0 degrees of freedom. So the atom balances here have the simplest degrees of freedom, right? The only thing that's tricky about them is things like hydrogen and nitrogen, which are diatomic molecules, but also elements in themselves. So notice this is an N balance. This is not an N2 balance. This is an N balance. Nitrogen atoms. In equals out. Feeding into the system, what are my sources of nitrogen? It's just the nitrogen diatomic gas. Okay, so that is going to be 25 moles per minute of N2 being fed to the system. But for every 1 N2, I have 2 nitrogens. Okay, make sense so far? Leaving the system, I have the number of moles of N2 that I don't know, okay, because there's nitrogen contained in that. And then I'm going to have 2 nitrogens for every 1 N2. So the only tricky part of the atom balances is making sure you convert from molecular species to atomic species, plus the number of moles of ammonia. And for every 1 ammonia, I get 1 nitrogen. So I can write this as NH3 if I want here. Right? 1 NH3 gives me 1 N. So now I've converted my molecular flow rates to atomic flow rates. That's what these conversion factors are here for. Does that make sense? This is the tricky part, is remembering to multiply by how many atoms are in the molecule. That's the only trickery in the atom balance. The H balance, again, H atoms, not H2 molecules. Yes?
So the reason it's a 1-to-1 ratio is because ammonia has 1 nitrogen in it?
Yep, ammonia has 1 nitrogen and 3 hydrogen, so we're going to see that the conversion for the hydrogen is going to be different. So for the hydrogen balance, let's just put that out there, 75 moles of H2 per minute. Right, and I'm putting all the units here in all of their rigor just to drive home the point that these are the atoms, not the molecules. When I do these types of problems on my own, I don't write out this necessarily, but oftentimes I do. I might just do 2-to-1. Right? I just might 2 over 1 or 1/2 or something like that. But for the purposes of this, for the notes, you get, for 1 H2, you get 2 hydrogen atoms. Out, leaving the system, we don't know how much hydrogen we have leaving, but we know that for every 1 hydrogen molecule, we get 2 hydrogen atoms, plus our unknown of ammonia. For every 1 ammonia, we get how many hydrogen atoms? 3. So this would be 3 H's. Okay? So again, if we steal the information that we've already worked out, that Na is equal to 25 moles per minute from the 50% conversion, we can now solve both of these equations. Right, so if you'll notice, this one has 2 degrees of freedom, 1 degree of freedom, 1 equation, 2 unknowns. 1 equation, 2 unknowns, so we need that design specification of the conversion in order to solve the rest of this problem. And then from here, if we plug it in, we should get the same results. Okay, questions? So these are the 3 strategies that we will be using in the class to balance reacting systems. So I want to give you a roadmap of what we're going to be doing. So throughout the class from here on out, we are going to be getting multiple units in your balances. They can have reactions or they could not have reactions. Some unit operations may have reactions, some may not. Okay? Currently, you're going to be given the compositions of the outlet streams, for example. The next stage, once we conclude material balances, is going to be our thermodynamics section. So I'm not going to tell you that the outlet air has 3% water. I'm going to say the outlet air has a relative humidity of 70% at this temperature. We're going to use our thermodynamics to figure out, well, by thermodynamics, what would be the outlet composition. I'm going to say you're going to go into a flash separator that follows Raoult's law. And then you tell me what the outlet composition of those streams are. right? Because then that allows us to begin to control the unit operations like a real process engineer would. What temperature and pressure do I operate this tank at to get my compositions of the outlet materials to be a certain value? So we're marching towards making the calculations more complex, but more relevant to the real world. Once we wrap up our thermodynamics, that tells us the composition, that tells us the equilibrium constant. Then we're going to move into telling the system how much energy does it take to operate this. Do I need to put energy into this chemical reactor to get it to that temperature? Do I have to take energy out of the system to get it to a certain temperature? So then, as chemical engineers, what we are being controlling, and this is what we get to control in the real world, how open and shut a valve is. Okay, that controls our flow rates. What is the pressure of the system, and what is the temperature of the system? That's all we get to control. And then by using our engineering principles, we should be able to suss out, hey, if I'm at this temperature and this pressure with this catalyst in this big of a tank, I should be able to make this flow rate of my product, and I should be able to sell it for this much money. Hey, let me seek $500 million of an investment to add on this new unit operation to our plant, right? So we have to do all this on paper because I can't buy a breadboard, right, like electrical engineers do and start to build my process. It doesn't work that way. Most of the process materials that we work with are flammable, toxic, expensive, right? Everything's really difficult. It's not like cutesy little resistors and robots, right? So chemical engineering sucks in some regards because we can't do as many of those hands-on things. But the good thing about chemical engineering is that if we can tolerate the virtual aspect, that trains us to be better than the other engineers, right? Because we can handle the uncertainty. We don't need to see the robot in front of us to know that we can build it, right? And even if you design and build a chemical plant, you ain't building anything, right? You're sitting in your office and you're watching the construction workers build the actual thing, okay? You're not turning the valve. You're telling the computer to turn the valve. So it's a little bit less fun if you love the hands-on monkey wrench and stuff, but we all have time for hobbies, right? But the nice thing about chemical engineering is that if we can train ourselves to operate in the abstract and the virtual world, we can solve more complicated problems than just simple engineering ones. Right? That allows chemical engineers to be very adaptable to a large number of finance or other management disciplines because we already have the years or decades of training to think about complex virtual problems that you can't sink your hands into. All right? So I'd like to view that as an asset and sort of explain why the chemical engineering class that introduces you to all the fun concepts is chalkboard work, right? Okay? All right, quiz on Friday. Please focus on your homework and talk to you later.